was a little bit maybe it was a little bit rushed, so we're going to dwell on this at the moment, and I'm going to show you a good worked example from one of the previous exams. So this is the last kind of element in the inner product spaces chapter, and it's called the Gram-Schmidt orthogonalization process, and it's a procedure. It's a procedure that takes a basis, any basis for a okay, thanks. It's a procedure that takes any basis for a certain space and gives you back a nice basis for that space. You can describe it colloquially as it straightens out the basis, meaning that it gives you back a basis where all the vectors are mutually orthogonal. This is the property possessed by the nice standard basis of the 2- and 3-dimensional vector spaces that we're very familiar with, like the IJK and V3R, the standard basis, unit vectors pointing along the X, Y, and Z axes. They're all mutually orthogonal. Each one is orthogonal to the others. Well, this procedure takes any old basis. So a generic basis will not consist of orthogonal vectors. They will just be vectors that span the space in question. So this process gives you back, as I say, a straightened out basis, an orthogonal basis. And as you can see, there's a recipe or a specification for it here. It does it all in terms of, so the U's are the old bases. So the new V1 is the old U1. Then after that, after getting started, each new vector, say the new V3, it's defined in terms of the old information, the U3s, and the previously constructed new vectors. So the V1 is appearing here, the V2 is appearing here. But those have already been constructed by the time you get to construct the V3. So it's like a generative procedure, a building procedure. And the other key ingredient, of course, is the appearance of the inner product. The basis that pops out at the end, we want that to be an orthogonal basis. So it's not surprising to see these various kind of compensating and rescaling terms introduced for each VI in terms of the inner product. And it's the inclusion of these terms that will ensure that the new basis, V1 through Vn, is a mutually orthogonal basis. A final procedure that is often asked for, so once you get your new basis, which is will then consist of mutually orthogonal vectors, a final step in the process of making a nice basis, which is often called for then, is to normalize everything. So to take all of the vectors and rescale them if necessary so that they all have standard length, that standard length being 1. Okay. So to show you an example of the application of this, I thought we'll continue our treatment of the past examination papers. So if I go back to the Moodle area and look at last year's paper, so this will finish off all the questions of 2016 that we've looked at with Stephen and myself. Here's the final part of question 8. Is a question based on this. So we're going to have a go at answering this now, and we'll talk through the various steps that we go through to complete the task, and we'll also have a look. There's also a nice compute, because this is just in 3 dimensions. There's a nice visualization of this that we can produce that will help to illustrate what has been going on, okay, and to help you kind of understand what the orthogonalization process is doing. So this deals with V3R. I'll just copy down the details of the question, then we'll switch to the overhead. And this has a basis consisting of the vectors 1, 3, 0, -1, 0, 1, and the third one is 1, 0, a half. These are three vectors. They're certainly not all of length 1. They don't particularly look like they're mutually orthogonal. They do kind of look like they're linearly independent, though, because the presence of the zeros in the different positions kind of suggests that these are going to be linearly independent, maybe. So the question is to apply the Gram-Schmidt process to get a orthogonal basis for V3 out of this. 2016, question 8, the last part C. Apply GS process, the Gram-Schmidt orthogonalization process, to obtain an orthogonal basis. For V3R. So we'll take it that these, to match it to the notation and the language of the specification in the book, we'll take it that these are our old vectors, U1, U2, U3, and the process specifies how to build a new basis. So this new basis will be V1, V2, V3. I'll underline my vectors. And the first step is kind of the easiest process. First new vector is just the first old vector. There's nothing yet that has to be orthogonal to anything else, so we can just take the first vector as the first vector from the original. Of course, the inner product here, and we weren't told anything else, so the inner product to use here is the standard inner product for this space, and the standard inner product for this space is just your well-known favorite inner product, the dot product. Okay, so the product of the sum of products of corresponding entries. So you see, in order to form V2, we will form this equation here, which is V2 is the old U2. Well, so I won't speak in terms of inner products now, I'll write this all out in terms of dot products. So the U2 with the new V1, and then finally the dot product of V1 with itself. And you're taking this multiple of V1. So although the expression for V2, the new vector V2, is referring to other new vectors V1, that's okay because the V1 has already been constructed. We already know what the new V1 is. Okay? We don't have any problems that the formula is referring to things which haven't been constructed. Okay? So some of these values we need to work out. So V1 with V1, that's the dot product of 1, 3, 0 itself, which would be 10. The sum of the products of corresponding terms, so it's 1 times 1 plus 3 times 3 plus 0, 10. And the U2 dot V1, so U2 is minus 1, 0, 1, and the V1 is this 1, 3, 0. So that's just minus 1. So V2, the old U2 is minus 1, 0, minus 1, 0, 1. Minus, so this ratio, so we're dividing, we're taking minus 1 over, 10 over minus 1. No, minus 1 over 10. Times V1. V1 has already been constructed. This is 1, 3, 0. So you just add those two vectors together. So in the first component, first is going to just be plus 110.
We've minus 1 plus 1/10, so that seems to be minus 9/10. We've 0 plus 1/10 of 3, so that's plus 3/10. And lastly, we've 1 plus nothing, just 1 at the end. Or if you maybe wanted to present that slightly better, you could take out the 10th. Then at least the thing has small integer entries. Taking out any fractional parts, maybe a nice way of presenting vectors. It's not necessary, of course, but it makes the presentation a bit easier. So there we've successfully generated V1 and V2. Okay, so we can again then go for V3. So the vector V, the new vector V3 is, it's basically the old vector. Basically the old vector U3. Of course, we've no guarantee that U3 is going to be orthogonal to either of the ones that have come before it. But by introducing the following corrections, that's what ensures it is going to be orthogonal. So we got minus the dot product of U3 with V1 over dot product of V1 itself. This is multiplying V1 and the vectors, and then we minus U3, the other new vector, V2, all over the dot product of V2 itself, and we're subtracting that multiple V2. Okay. Now we'll fill in these values in a moment according to the formula, but this might be just a good point to stop and pause and just try and appreciate the reason for why these things are constructed like they are. Okay? The point is to produce a new set of vectors V1, V2, and V3, which are mutually orthogonal. We've already constructed V1 and V2. So this V3 is supposed to be orthogonal to V2 and V1. So if you try testing that out in your mind at this stage, or making a few notes, how do I test if this new V3 is going to be orthogonal to V1? I have to take the dot product between the two vectors. The definition of orthogonality for vectors in this context is that the two vectors have a dot product of 0. So if I take the dot product of V1 with V3, well, that's the same as the dot product of V3 of V1 with the right-hand side. Okay? The right-hand side refers to stuff that we already have, either the old vectors U3 or the previously constructed vectors V1 and V2. So if you look at what happens is you take the inner product. Remember, the inner product, or the dot product in this case, is a function that's linear in both variables. So if I want to take the dot product of V1 with this whole expression, which is a sum of 3 vectors, this U3 plus this multiple of V1 plus this multiple of V2, I want to take the dot product of V1 with all of that. I just take the dot product of V1 with each of the individual 3 vectors and add the results together. Now, starting from the right here, as you take the dot product of V1 with this vector here, well, this vector here is a scalar fraction of dot products, a scalar multiple of V2. But we already know that V1 and V2 are orthogonal, because that's what the procedure claims to show. So by induction, we already know that V1 is orthogonal to V2. So the dot product of V1 with V2 is going to be 0. So you don't get any contribution from this. When you take the dot product of V1 with this second part, again, this is a scalar multiple of the vector V1. So you take the dot product of V1 with V1, you get a certain value, v1 dot v1, whatever it is. It's the square of the length of the vector v1. But you also see that term appearing here in the denominator. Dot product of v1 with v1. So after you do dot product of v1 with v1 here, it cancels with this term in the denominator. And you're just left with the negative of v1 dot v3. Okay, that's made some contribution to the overall dot product. You then take the dot product of v1 with the last bit, which is u3. So you get the dot product of v1 with u3. But just a moment before, we got minus the dot product of v1 with u3. So it's by construction, by design, those two are going to cancel out with each other, and we finish taking the dot product and we're left with nothing. So we're left with a 0 on the right hand side. So we can appreciate here how it comes about that this new vector we're constructing, v3, is by design orthogonal to the vector v1. Okay. We know v1 is orthogonal to v2, so dot product of v1 with this is 0. Dot product of v1 with this, well, it's with itself here, and that cancels out that factor, so you just left with minus u3 v1, which will cancel with the plus u3 dot v1 that you get when you take the dot product. So you can appreciate the reason for, why it is that those parts, why it is that those corrections are made to the old third basis vector in order to ensure that this new one we're designing is orthogonal to the previously constructed. Exactly the same argument would apply here if you take the dot product of v3 with v2. Just take the dot product of v2 with each of these 3 bits. It's going to get nothing here, since it's the dot product of v2 with v1, and by induction they are orthogonal. The dot product of v2 with v2 cancels with this denominator. You're left with minus u3 v2, but then you get a plus u3 v2 when you take the dot product at this point. So in total, you get a dot product of v2. Okay, so you can kind of get a feel, or you can see the operation of why these things are mutually orthogonal. Okay, but there's a number of any questions? Okay, so there's still a number of ingredients we need to assemble here. We've got v1 with v1. We previously got that. That was 10. So we'll need u3 with v1. So v1 dot v1 is equal to 10. We've already got that. u3 dot v1 is the dot product of u3, which is 1, 0, 1 half, with v1 is 1, 3, 0. So that's just 1, isn't it? Dot product. And then we need v2 with v2. v2 with v2 is going to be a bit messy. So you're going to have taken the dot product of this vector here with itself. It'll be something over 100. 9 squared, which is 81, plus 9, plus another 100, plus 90, 190 over 100. 19 over 10. Okay, not too bad in the end. 19 over 10. Okay, and then the last bit you need is u3 with v2 for that numerator. So u3 is 1, 0, 1 half. v2 is up here. This is this 1/10 of minus 9, 10. When you take the dot product of those, you have a 10th, and minus 9 plus nothing plus a half 10, which is 5. So minus 9 plus 5 gives you minus 4. So minus 4/10 or minus 2/5. Okay. Now you got all the ingredients, so now you can write down v3. u3, which is 1, 0, 1 half. Minus this ratio, u3 with v1. Did I not do that? Oh yeah, v3 with v1, which is just 1, easy enough.
V1 with V1 is just 10. And it's this multiple of V1, which is 130. Then minus this ratio here, V3 with V2, minus 2/5. 2 with V2 was 19 over 10. And it's this multiple of vector V2. It's there. It's itself 1 over 10 minus 9/3.
So you get into the later stages of these, you get more and more terms and all these fractions. So potentially, just have to tread carefully. So let's see what we got. Well, first of all, that 10th will cancel with that 10th there. This is below the line. This is below the line. So those 10s go, which is nice enough. Then you just go component by component, see what you got. So you got 1 minus a 10th, which is 9/10. I might just do this in stages. So you got 9/10, and then we're minus, so we're plus. But there's a minus there, so it's going to be a minus something. So you got 18 in the numerator. And 5 by 19, which is what, 95 in the denominator. Okay, fair enough. And the middle one, you got nothing, thank God, minus 3/10. And something is going on here. It's negative, so it's positive. And it's a 3 by 2 is 6. Again, 5 by 19, it's 95. Last component, you got a half there, nothing, and something here, negative, so it's positive. And it's 10 by 2 is 20 over 95. So unfortunately, we got to combine tenths and 95ths and halves and 95ths, so you have to basically go to 2 times 95. 2 times 95 is 190. Oh. Damn, I die of migraine if I attempt to do this in front of all of you. So
169.
yeah, go. Call it out. So what's the numerator in the first position?
169.
Good. Second position?
Minus 45.
Good.
135.
Good. Thank you. Save my life. Thank you. And 190 is the denominator? Yeah. Good. Okay, no, you can't cancel that there because 169 bit. So those are our vectors. Our new vectors, v1, v2, v3. Now the claim is that v1, v2, v3 are now mutually orthogonal. Okay? And indeed, if you started testing out dot products there, you should find that all the mutual dot products that you work out are zero. There's an interesting, which I'd like to do for you now, is to visualize this with using the computer to plot these vectors. Right one. Because when you plot it, you also perceive other aspects of the construction as well. So this is quite
readily done with Sage, but you could certainly do equivalent work with MATLAB if you wished. So I'll just get a worksheet up and we'll ask it to plot these various vectors for us. And I'd just like to emphasize, like, it's a good example of using either Sage or equivalently MATLAB or whatever to kind of help you think through these problems and to visualize them and so on. Okay, so our first vectors were U1, U2, U3. Quickly get these typed in. So this is how we define. So Sage has a natural vector like vector objects in it that it understands. So vector 1, 3, 0, U2 was -1, 0, 0, 1. And U3 was 1, 0, 1/2. And then we can set B to be our old basis, U1, U2, U3. That's just B as a list of those three vectors. So that looks right. We've got these three vectors. That line just initializes P to be a blank graphics object, which we can add on graphics elements. So we do P equals P plus, so the basic graphic element we're adding on is a plot of the vector U. And this is a Python for loop construction. So we're saying for every vector U in the set B, which we just defined, add on to P, started off as blank, so it'll accumulate graphics objects, add on a plot to U. So we just do that. So that builds P up as this compound graphics object. Then we can just have a look at P. So what P should be is just a graphics object containing these three vectors, okay? So you just get this nice 3D visualization, and we can tell from looking at that those three vectors are linearly independent, okay? Because they're pointing in mutually different directions, okay? While it does look like the third one, or the horizontal looking one there, while it does appear that this horizontal looking one is orthogonal to the previous two, it is at right angles to the previous two, but those first two don't look like they're at right angles. The angle is a bit bigger than a right angle. So there is certainly some non-orthogonality going on there, okay? Okay, so then we get the new vectors. So we'll type in what we got. So this will kind of do a visual check in our calculations. I could calculate them using Sage, but I'll just take the values we got. So the first new vector was the same as the previous old vector. Vector V2, I'll type that in. So it was 1/10. 1/10. No, sorry, V2 was, sorry, -9/10. 3/10 and 10/10 or 1. And then V3 was the one with 190, so it's 169. Divide 190 minus 45 over 190, and 135 over 190. Okay, again, I'll put those three vectors together in a list called the list BB, the new version of B. And then I'll continue adding on for every V in BB, continue adding on plots of these vectors into the graphics object P, except this time I'll plot them with a color of red so we can distinguish them easily from the previous ones, which were blue. So again, that's a Python for loop. This construction plus equals is just a shorthand for P equals P plus this. Just allows you to not have to type P a second time. So execute that. That quickly runs through that loop 3 times and develops P. Okay, so this is the outcome of the whole procedure. Ah, yes, okay. So where's the second blue vector gone? Or where's the third blue vector? So you can see that this large red vector is actually the same as the large blue vector. So they're both superimposed on each other. Since the red vector was added second, it's obscuring the blue vector. So this was actually our U1. So U1 and V1 are the same. That's why we can only see the red V1. It's lying completely over the old U1. And the difference here is, okay, so U vector V1 is still orthogonal. So actually, sorry, I misspoke before. The old vector U1 was not orthogonal to the old vectors U2 and U3. But you can see here how the new vectors are orthogonal. So when we organize, when we take the view of it where the vector V1 is pointing straight up the page, both V2 and V3, whichever ones these are pointing exactly horizontal. Okay. So the vector V1 is orthogonal to those two. And when you look at it from the other side as well, twist it around a bit until you get a good view of it, you can see that the other two vectors, the V1 and V2, these red ones here, see if you tilt your head or if I could rotate the plot around, that those are now mutually orthogonal as well. Okay. If we just add another step into normal, so I said often there's an extra step added in to working with the Gram-Schmidt orthogonalization process, and that's to make the basis even better still, to make it almost exactly like the standard basis. So as well as them being mutually orthogonal, make them all standardized in length as well. So that means to divide them all by their magnitudes. So if I defined V1 again there, and I think it's probably V1.norm. We'll give you the norm of that, multiply that by V1, and just set V1 to be equal to that. And do the same for V2 and V3. Could have done that with a loop as well, but. So you're taking each vector there and dividing it, taking the scalar multiple of it by 1 over its norm. And then set BB equal to V1, V2, V3. Okay, so that looks like a mess, but it does look like the right kind of mess because you've loads of square roots in the denominators and so on, and lots of fractions. So that's showing that all the vectors have been normalized. So if you then add those using this new, what is now an orthogonal, but also a normalized basis. Yeah. So from the original typical or average or random basis of the original blue vectors, we've got, what looks like a much better, well-behaved basis for the same vector space, which is this red basis. Okay. You can easily appreciate how that by rotating it around and looking at it, how that's the basis of mutually orthogonal vectors, the red triple, and how they're all been, how their lengths have all been standardized. So they've all got length 1 there. Okay. What is also apparent, which you can see from this construction here, is as well as, I mean, you might ask, what's the point of this process in the sense that what's so great about building the new basis out of the old basis? Surely we could just discard the old basis and just jump to our favorite new basis. Well, this procedure just also has the advantage that as it builds up the new basis, it's preserving the intermediate subspaces that you have. Now, what I mean by that is, so this long blue vector was the original vector u1 in the equation. Okay? The new vector v1 that's produced is just a scalar multiple of that. So it still points in the same direction. So the subspace generated by the first old basis vector u1 is the same as the subspace generated by the new vector v1, by the new first vector v1. And you then look at the new second vector. So the new second vector is this upward pointing one here, right? That red vector. And its partner, old second vector, is that blue. Now what's preserved there is that if you look at the subspace generated by the first two vectors, so the first two blue vectors are the two vectors in the right-hand half. This first blue vector and the second blue vector, pointing up to the top right. The subspace generated by those two first old basis vectors is a plane. Okay? So imagine the plane is spanned by the first blue vector and the second blue vector. The first and second new vectors in red there, they span exactly the same plane. So that intermediate subspace there, so you can see when you look at one of them head on there, you see that the new vector v2 is exactly collinear or superimposed on the old vector u2. So the plane, the subspace, the plane, which is a subspace of v3, that's spanned by the old vectors u1 and u2, which are the two blue upward facing blue vectors there. It's exactly the same as the plane spanned by the new v1 and the new v2. Okay. And then obviously when we add the third vector in, we get the whole of the three-dimensional spaces, the subspace generated by the three vectors. But if you're in a higher dimensional setting, so where you had lots of these vectors to construct, if you stop this process at any stage and you asked, well, what's the vector subspace spanned by the first four new basis vectors I'm generating? What is still true is that the vector subspace spanned by the first four new vectors, it's going to be the same as the subspace that was spanned by the first four old vectors. So the orthogonalization process builds up the new basis, respecting or preserving those intermediate subspaces that are spanned by various, initial segments of the old basis. Okay. So, I mean, if you were given an old basis and you were completely uninterested in it and you just wanted to bounce or jump to a nice new basis for the space, yeah, just completely discard the old basis and just take on whatever nice new basis you care about or have available. But in many applications, it might be important, to preserve certain information about the old basis, okay? And information that the old ordered set of vectors has within it is this kind of stratification of the space. In building, just taking the first basis vector gives you a one-dimensional subspace. The first two basis vectors gives you a two-dimensional subspace. The first three gives you a three-dimensional subspace, and so on. So you get this kind of stratification of the whole space, building it up one dimension at a time as you add in each new basis vector. Okay, but your basis might be a bit unwieldy in the fact that they're not mutually orthogonal and they're not normalized in length. So the new basis you get out from this process here is orthogonal, and you can then go on to rescale them to make them all of length 1. But what's still preserved is this stratification of the space. So U1 and V1 are actually both the same vector, or they're both pointing in the same direction. U2 and V2, they still span the same subspace. So the second intermediate vector subspace is still the same in both cases. And the U3, V3, as you add in each new vector to each basis, it's the same subspace that's spanned in both cases. So that's really what the Gram-Schmidt process is giving to you, and why it might be a useful thing to build a new basis out of an old one. Okay. Is there any questions or clarification on that I could give? Okay. Well, when I see you again in a couple of hours, I'll take another past paper example, and maybe another example of applying this Gram-Schmidt process in maybe a different context and so on. Okay, we might leave it there for now, but if you've got any individual questions, feel free to come up.